So the topic is on superposition theorem, and it's a very useful theorem used when there are multiple voltage sources. And an example of a circuit with multiple voltage sources might look something like this. I may have a resistor. I will call this point A, point B. Let's label this R1 and come over here. This will be a point C. This will be a resistor right here. This will be an R2. This will be an R3. I will put a voltage source here, and I will put a voltage source over here. And this would be VS1 for 5 volts. This will be VS2 at 3.3 volts. This will be 100 ohms. This will be 220 ohms. Sorry, 220 ohms. This will be 330 ohms. This will be a point D, point E, and point F. Wow. So as you look at this, this is kind of reminiscent of series parallel. If we didn't have a second voltage source, this would be a straight up pretty easy, we hope, series parallel circuit for you to resolve. How would you resolve this? This would have been in a simple series circuit, something like this. We would have had an R1, we would have had an R2, R3 with a singular voltage source, boom, 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 like so. So without the second voltage source, it could have looked like this, VS1 at 5 volts, and then the 3 resistors. How would you solve this? We've done this several times. You would do a redraw, yes? So in a redraw, you would simplify the 3 resistors into 2 resistors. So you look at the circuit from a point that is farthest away from the voltage source, and you look for relationships that you can see between these resistors. And what relationships do you see, Yusuf? How can I redraw this to become a simpler circuit?
R2 and R3 are in parallel, so R equivalent 1.
R2 and R3. You're right. I would draw this directly beneath the original circuit and place VS1, 5 volts. My R1 is here. So point A, point B, point C. That's not point C. This would have been point E and F. E and F. So here is A. And right over here, in place of these 2, I would have a single equivalent resistance. This would have been called REQ1, and this would have been equal to R2 parallel with R3. And then you go about your merry way of solving this, as we've done several times already. Introduce to this another component, another voltage source, like this. If I introduce a voltage source here, then this takes on a different dimension with respect to solutions, because I now have a second voltage source influencing the current flow of what's going on with this. So when we're playing with something called superposition theorem, this is specifically designed for circuits where there happen to be multiple voltage sources, and I have 2. And there's a very specific way, very easy way of solving these. The very specific steps that we will engage will be the following. So to solve, the steps are, number 1, replace VS2 with a short and VIR. So you are going to create a table for voltage, current, and resistance. With this guy being replaced with a short, you do a complete VIR. And you've done that before. It would look something just like this. You replace the voltage source number 2 with a wire, and you do a VIR for what's left. And this is, as I said, you've had plenty of practice doing this, and we'll do this together in a moment. That's step 1. After you complete the VIR for step 1, then number 2, return VS2 and replace VS1 with short and VIR again. So what that means is you're going to bring back in VS2 exactly as this is drawn. But where VS1 is in this drawing, I'm going to put a bare wire in there. And by putting a bare wire in here, it becomes, again, a simple series parallel circuit, and you do another VIR chart for this. What's different about your VIR in each of these instances, when you do the VIR table, you're also going to plot, you're also going to record direction of current. And same thing here. When you do this VIR, you're also going to record current directions. Then the very last thing you do in step number 3 for superposition is you will combine and algebraically combine VIR and current directions. Okay, so those are the 3 very basic steps, and I've kind of shortened this up. We will be reviewing each one of these in detail. It's the procedure that we've been practicing so far in series parallel circuit reduction is going to help us out quite a bit in this exercise. So keep in mind, when you're doing superposition, there's 3 steps. You replace one of the voltage sources with a what? A short, and then you do a VIR table, and be mindful that you want to record the direction of your currents. Then in step 2, you want to return that voltage source because you had it shorted. It was replaced with a wire. You want to bring it back. When you bring it back, it looks just like this. And then you want to replace your first voltage source with a short. So you put a short wire here, and you do another VIR table and record the current directions, whether it's up, down, left, or to the right. Then the third thing is you algebraically combine your VIR data and your current directions for a final, and that will give you the final analysis of what's happening in this circuit. Okay, it's a really good exercise. It's not a hard exercise, but it is some parts of it are going to be repetitive. So let me go ahead and begin this with you here. So we said in this exercise we are going to replace this guy with a short. So I'm going to redraw this.
Voice test on 20, voice test on 20. Luke, are you there? Over.
Okay, let me turn down their voice test. Thank you. All right. So in here, I have replaced this with a short. I'm going to analyze what's going to happen with this. So I'm going to fill in the data. This is 100 ohms. This is 220 ohms. This one's 330 ohms. We said from earlier that these two combine to give us an R equivalent of these two parallel with each other. So let's go ahead, pull out our calculators and make this calculation. Let me grab a calculator. And so 220 and 330 combined in parallel. Wei-Ji, what does that calculate to be?
220 reciprocal plus 330 reciprocal, and then reciprocal the sums.
Correct. That's the process. And what is it that you calculate?
132 ohms.
132 point what?
Exact 132.
Wow. Okay. It worked out to be exactly 132. And yes, the calculator does verify 132 ohms. Cool. And we happen to have this guy in series with R1, yeah? So if it's in series with R1, and R1 was one of the original circuit resistors, it was 100 ohms, then what is my RT as a result of this part of the analysis? Simply 100 plus the 132 should give us what, 232 ohms? Is that right, my friends? Okay, so we have 232 ohms. Now the VIR for this is going to be very similar to what we've done before with one slight modification. The VIR, V-I-I-R, I'm going to have two columns for I, two columns for I. You'll see why in a moment. This will be for R1, this will be for R2, this will be for R3, and this will be for totals. And we don't need to calculate everything, but we do need some components that are necessary. So for R1 was 100 ohms. R2 was 220 ohms. R3 is 330 ohms. And the total came out to 232 ohms. And the voltage source on this side that we're left with, VS1, is 5 volts. So we have 5 volts. Everybody okay with this so far? Because what we're going to put into the double I column, one will be for direction, and we're going to say electron flow. Electron flow direction. We're going to use the electron flow model. And these will be in either milli or possibly microamps. We haven't calculated this yet. So our values, numerical values will go here, and then our arrows will go here, okay? The voltages are not significant for us at this point in time, interestingly. So we have 232. Based on this, could we calculate the amount of current that flows in the circuit? We can. We happen to have 5 volts at 232 ohms. Let's go ahead and calculate the current. And Jackie, what do you calculate the current to be when you take 5 volts and divide by 232? Hold on, she's getting her calculator. That's quite all right.
21.55 milliamps.
21.55 milliamps, I concur. So we will go ahead and mark that into our schematic. It's really helpful to draw that in right here so you can see the current that flows. And this is the direction of electron current flow, yes? Don't the electrons leave the negative side, flow through the circuit and come back? Now, electrons, when they flow through a component, they flow from what polarity to what polarity? If you recall in your notes, electrons always flow from the negative side of a device through it to the positive side of that device. So as the electrons are flowing from the right side to the left, it always flows into what polarity on this side of R1? Always flows into negative and comes out on positive side of that device. That's the nature of electron current flow. And if you look at the polarities, do I have the positive side of this resistor matched with the positive side of the voltage source? That's an affirmative. Do I have the negative side of this resistor matched with the negative side of the voltage source? That is also a yes. So we're happy with how the polarities have worked out in this particular drawing. Can you make a determination right now of a value of current and a direction of current in this drawing that could help us fill in some of the data in this table. What do you think we can fill in? Wei Ji, do you have a suggestion what we can fill in?
Yeah, we can fill in the I total and also the R1, the I1. IR1, sorry.
Okay, good. That's spoken correctly. We can fill in the total current as well as the current through R1, because that's one of our original circuit resistors, and it clearly flows through R1. So we, in other words, in here, we can take our calculated 21.55 milliamps for total and fill this in for 21.55 milliamps for R1. So far, so good? Okay. And is there a direction of current that I can fill in here? What we won't fill in on these tables will be this. We will not fill this guy in. That won't be necessary. And at this stage, we won't need to fill these guys in either. That's just extra work. So we're really interested in I total and the currents through the branch resistors and then directions. This is the critical information we need for superposition. So do I have a direction of current flowing through R1? Can I draw that arrow based on what's here? Is that arrow flowing up? Is it flowing to the left? Is it flowing to the right? Is it flowing down? Which way are the electrons flowing through R1? Jackie, what do you think?
They're flowing to the left.
They're flowing to the left. It goes in the right-hand side, through it, out the left-hand side, from the negative to the positive. Is everybody in agreement that the current through R1 is to the left? And that's what I'm going to do. I'm going to put in an arrow that shows to the left, big arrow. That part's done. Now you're tasked with determining the branch currents of these two and their directions. You've done this before. So what we do, since we've analyzed the series circuit enough that allows us to fill in this cell, and this cell, we now have to work on R2 and R3. So that means we have to take this information that we've just calculated and now bring it back upstairs to our circuit. So negative, positive, and the current that flows out here is our 21.55 milliamps. What happens at node E, Yusuf? What happens when the current, when total flow, it divides, it splits? You're correct. Those two words are both correct. We have a current that clearly flows up through R3, and we have a current that clearly flows to the right here. What happens when it hits this corner? It will flow up. What happens when it hits this corner? It will flow left, like so. Yes? And so can we mark the direction of current flow for R2 and R3 based on what we've done here? What is my direction of current flow for R2? Is it left, right, up, or down, class?
Left.
Left, 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 left for R2. Okay, left for R2. How about the current flow for R3? Up, down, left, or right?
Up.
Up. Okay, that's a very critical piece of information. We now have those three current directions. We just need to figure the amounts. How do we figure the amounts of the current? We said that the current splits, the current divides. So the inclination is to use what method here?
The current divider formula.
Current divider formula, I would support wholeheartely. And for current divider formula, let's go ahead and do this. CDF for current divider formula. And keep in mind, IRX is equal to RT over RX times I total. That is the general form of the current divider formula. How are we going to apply that specifically to R2 and R3? We're going to do this. So my IR2 is going to be equal to, now what expressions am I going to write in this formula, Yusuf, for IR2? Not values, but what expressions am I going to write? The formula says RT over Rx. What am I going to do for my numerator and denominator?
So you want IR2 equals R1 equivalent over whichever resistor you want. You want R2 probably.
Yes, there we are. That is correct. If we want the current flowing through R2, we have to take not the total resistance of the circuit of 232, but the total of what is in parallel. And the total of the two resistors in parallel was REQ1 of 132 ohms. So this is how we set up our formula and then multiply by IT. And so now we will fill in the numbers. REQ1 was 132, and this will be over 220. And now we're going to multiply this by our, what do we have, 21.55 milliamps. So Yusuf, you calculate IR2 to be what value when we go to do this calculation? On clear 132 divided by 220 times my current. And what did you calculate, my friend?
12.93 milliamps.
Okay, and my calculator confirms you're 12.93, and you can see the milliamps right there. So it works out to be 12.93 milliamps. That's very good for IR2. We need one more current. We need an IR3. How do I set up the formula for IR3, Jackie? What terms do I use in the numerator and denominator?
You would use 132 over 330.
132 over 330 times my 21.55. And so what is it that you end up calculating here? 132 divided by 330 and times, grab that current, and you calculate what value?
I calculate 8.62 milliamps.
And everybody, can you see my calculator confirms hers at 8.62 milliamps? Yes? So 8.62 milliamps right there. So now do I have the two branch currents? And as I analyze this, do these currents make sense? Just because you've got numbers, let's see if they make sense. IR3 was 8.62 milliamps. IR2 was 12.93 milliamps. Which branch has more ohms? R3 has more ohms. Should it have the lower current of these two currents? Yes, it does. This is the smaller ohms of the pair that are in parallel. Should it have the higher current? Because less ohms means higher current, and this has the larger current of these two currents. So, and do these two currents add up to give us back our total of 21.55 milliamps? And if you go to do that, yes, they do. So we want to take this information and now write it into our table. And our table says right here that this works out to be 12.93 milliamps, and this was 8.62 milliamps. Okay. Are we okay with the data in this VIR analysis? This is our data calculated with V2 shorted. Is everybody okay with that? Now, that completes the very first step of superposition. The first step of superposition said we needed to replace VS2 with a short, do a VIR analysis, and record the directions of current. We replaced the source with a short, did a complete VIR analysis, and recorded the directions of currents in our VIR table. We didn't have to calculate for voltages. We don't have to calculate for total current. The most important information is this information right here. Done. Now we're ready for step 2. And in step 2, what was our directive? Our directive in step 2 was to return VS2. And so I'm going to quickly return VS2. So here is point B, here is R2, here is point C, here is VS2 3.3 volts. Here is my R3 of 330 ohms. There. And put in my first resistor, R1. And this is 220 ohms. This is 100 ohms. And point D, E, F, A, and VS1 is going to be replaced with a short. So I'm going to draw in a short. Boom, there we are. This is the beginning of your second VIR analysis. We return to VS2, make sure the polarity of the plates were as in the original circuit. Right here, there was positive on top. And we will replace VS1 with a short. Everything else remains in the same place as it did in the original circuit. We're going to, as we've always done in our series parallel circuits, simplify 3 resistors down to 2 resistors to a simple series circuit, yeah? And so here's my voltage source on this side. Where do I begin my look back into the circuit? A point that is farthest away from the source, which is this side looking in. And if I'm over here looking in, what kind of relationship do you see with respect to these resistors as we try to simplify this to a simple series circuit? Jacqueline, what do you think?
R1 and R3 are parallel with each other.
R1 and R3 are in parallel with each other. How many people agree with that? Wave, okay, cool. All right, so let's go ahead and do that. Here is, here, C, and we have this guy here, to here, D, and this is VS2 3.3 volts, and this will be a single equivalent resistance. We'll call this REQ1, and this is equal to R1 in parallel with R3, meaning here I have a 100 ohm in parallel with a 330 ohms. So guess what, Jacqueline? Guess what I'm going to ask you to calculate next, if you haven't already done this, is R1 of 100 ohms parallel with R3 of 330, and that works out to be what value?
76.74.
And I would concur with 76.74 ohms. Everybody okay? 76.74 ohms. Very good. And we match that up with one of our original circuit resistors, which in this case is R2, 220 ohms. Have we now taken the 3 resistors series parallel, reduced it into two resistors in series with each other? Is this easy for us to calculate an R total for at this point in time? Simply just add these 2 values, and your R total in this case should work out to be 296.74 ohms, yes? Everybody in agreement with that? So far, so good? Okay. Once we've gotten all the way to our total, let's go ahead and set up our next VIR table. So our next VIR table will look a lot like our first one. We have a V, double I, and then an R. And we have to have the same number of rows. So I'll do this as neatly as I can. R1, R2, R3 totals. We have V, I, and R. And so this particular column will be for electron flow direction. And this particular column will be for either milliamps or microamps, depending upon what we calculate. We can fill in the values. They haven't changed since our first time we played with this. So they will remain 100 ohms, 220 ohms, 330 ohms. But what has changed in our schematic? What's changed in our schematic is our R total. Our R total is now, whoops, wrong schematic. That's the right schematic. Our R total is now 296 ohms, 0.74, and our voltage source is 3.3 volts. So that means we have to fill that in to this appropriately, yeah? So our V total here must reflect our 3.3 volts. So I'll go ahead and do that. 3.3 volts. And our total ohms we calculated 296.74. So 296.74 omegas. Is this information so far the data that we've collected and calculated from here? So far, so good? Okay. And we said before, in this part of our superposition analysis, we can forego doing this particular sequence of cells, and we can forego this. So really, we really need the total resistance and these 7 cells, okay? So do we have enough information to find I total? We have V total, we have R total. Can we find I total? And Wei Ji, what does I total work out to be?
11.12 milliamps.
Okay, that works out to be, let's go here, 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 220 close. So 11.12 milliamps, yes? Everybody concur? 11.12 milliamps. Now, let's draw the arrows and polarities, how that works out in this series circuit. Plus, minus. So the electrons flow from the negative to here, flows up here, over to here, through this, and then back to the source, yes? And it is 11.12 milliamps. As we look at this simple series circuit, we've now determined IT. Have we also determined a value of current for one of the original circuit resistors and a direction of current for one of those original circuit resistors? Wei Ji?
Yeah, IR2. We also determined that.
IR2. And the current flows which direction?
To the right.
To the right. So in this table, we can fill in 11.12 milliamps for IR2, and it flows to the right. Is that correct? Is that information reflecting what it is that we have here? For R2, 11.12 milliamps, and it is flowing from the left to the right. So we draw it this way. Everybody okay with those two values and those two cells? So far, so good? Okay. Now, we're pretty much done with the series circuit. Once we're done analyzing what's happening in the series circuit, let's bring this information back upstairs. Let's bring it back up to this circuit, and see what happens with respect to this side of the schematic. So positive, negative, the current that flows out here and hits this node is 11.12 milliamps. What will happen at node E? It will split. Part of the current will go up, the other part will go to the left. Hits this corner, goes up. Hits this corner, turns right. So through R1, do I now have a direction of current through R1? Do I now have a direction of current through R3? What happens when these two currents meet at point B? They combine to go back to the source in that fashion. Everybody okay with those directions? So can we mark the direction of current for R1 as being to the right? R1 flows to the right. And how about the direction of current for R3? The direction of current for R3 is going upwards. So I'm going to go draw this upwards. So far, so good. Now I have to calculate the two currents. And the two currents are calculated using, again, current divider formula, like what we've done before. And so if I wanted the current that flows through R1 as an example, okay, if I want the current that flows through R1, let's go ahead and do that. So my IR1 is going to be equal to sum RT over R1 times I total. What value do I use in my numerator? What value do I use in my denominator? I already know my I total is going to be 11.12 milliamps. So do I use RT for the whole circuit that we calculated earlier, the 296, or what? Yusuf?
I think you're going to use the R equivalent.
We're going to use the R equivalent. We can only use the R total for that combination in parallel, which is this guy here, the 76.74 ohms. So 76.74, and that's going to be divided by the value of R1, which is 100 ohms. So in our paper, we will have 100 in the denominator and all of this. And so your calculated current as a result of all of this, Yusuf, what do you have there, my friend?
Which one? I'm sorry, are we on resistor 1?
Yeah, the current through resistor number 1.
8.53 milliamps.
And we concur with 8.53 milliamps. So 8.53 milliamps. Can I now fill in IR1 with 8.93 milliamps? 8.53 milliamps, and we already determined the direction was going to the right. Now we have another branch current to determine, and that is IR2. So IR3 is going to be equal to something over something times my total current of 11.12 milliamps. So Jacqueline, what is my numerator going to be?
Your numerator is going to be 76.74 ohms.
Correct. 76.74 ohms. And my denominator is going to be?
330 ohms.
330 ohms. So let's go ahead and do the math on this. Take our 76 ohms, divide by 330, and multiply by our current. And what do you calculate that to be, Jacqueline?
2.69 milliamps.
And it works out to be 2 point what?
So I got 2.69.
And you may very well have gotten 2.69. I was using memories of the yin-yang. Let's take a look. 76.74 divided by 330 times
Oh, no, you're right.
0.011.
I misread the 6 as a 9.
Ah, okay. And so, and then engineering. So it worked out to be, and if you, is this correct? 259 milliamps or 2.59 milliamps? Okay, so I have it on this calculator and then I also have it on here. So 2.59 milliamps. All right, cool. So IR3 equals 2.59 milliamps. And that allows us to fill in this part of our VIR table. 2.59 milliamps. Woohoo. Okay, so these are calculations with VS1 shorted. So all of this is what we would call part 2. The previous table was part 1. So part 1 gave us this information. Part 2 gave us this VIR information. And what was the thing that we needed to do for part 3? What's it say for part 3? It says how are we going to combine the VIRs? Algebraically. We're going to algebraically combine our VIR calculations as well as the current directions. And let me show you how easily that's done. So what I'm going to need is another piece of paper. I'm going to have that right over here. We're going to do this. This will be our part number 3. And so for part number 3, this is what we're going to have. For R1, for R2, R3 totals. I do want a pretty hefty column for V, because now I will calculate for V. I have I, and I have I, and I have R. So in this particular case, for our final, there will be no R total, and there will be no V total. There will be no I total. What we're going to be concerned about is what happens on all of our resistors. So let's go ahead and fill in the values of our resistors. So our resistors have and have not changed since we started with 100 ohms, 220 ohms, 330 ohms, and the, okay, yeah, we also won't be filling in this one either. We're really only interested in those 12 cells. All right, show you how we're going to do this. Let's take a look at our information from part 1 and part 2. And let's do these one resistor at a time. So part 1's paper is on top, part 2's paper is on the bottom. And let's just analyze what happens with R1. If we take a look at R1, and let me help block out some information here. If we look only at R1 and not be concerned with anything else, in one instance, we had current flowing to the left of this much current through R1, yeah? In a separate analysis, we had current flowing to the right of this. Well, these are these currents aiding each other, or are they opposing each other? If they're moving in opposite directions, they're opposing each other. If they're moving in the same direction, they're aiding each other. So as these are moving in opposite directions, they are said to be opposing. One's bigger than the other. Which one will win? The 21.55 milliamps, or will the 8.53 milliamps win? The stronger one will win. Your vote is with which one? Wei Ji?
21.55 wins.
This one will win. So that means the final current through R1 is not going to be to the right. The final current is determined by the larger current. So the final current must be to the left. And I will go ahead and draw that in for R1 going to the left. Did everybody see how that was reconciled? How did we reconcile the final current in part 3 is we look at the two currents achieved in part 1 and part 2 for R1, and they were antagonistic. This one is clearly larger. This direction is the final direction that wins. Now, because they are antagonistic, what is my final amount of current? My final amount of current would be this. The bigger one subtracts the smaller one. Did you hear that? The larger one subtracts the smaller one. Let's go ahead and do that. Let's go ahead and take our calculator, clear, and take the larger one, 2155, and subtract 853, and engineering. And do you all end up with what? Weiji?
13.02 milliamps.
And that's what I have on my calculator as well as 13.02 milliamps. So I will fill that in. The 13.02 milliamps. Wow, guess what? While you have that final current now, and that final current was determined by the larger current subtracting the smaller one. Why are they subtracting? Why are they not adding? They're not adding to each other because these currents are flowing in opposite directions. So the bigger one must subtract the smaller one. This is the difference. And the larger current direction gives us our final direction of current. Do we have enough information now to calculate the voltage, the final voltage? Isn't it I times R? So while this number is on your calculator right now, it is on mine. Hopefully it still is on yours. Multiply that by 100 times 100. And what is your voltage across R1? Weiji?
1.30 volts.
1.30 volts. Is everybody okay with the final amount of voltage across R1? Cool. Now we're going to continue the same process algebraically. Let's take a look at what's happening with R2. So let's slide down to R2 here and try to block some of this off up here so that that won't be confusing the issue. So we're only looking at R2, and now let's look at R2, and I'll try to block this as much as I can here. All right, so do I have an R2 with a amount and a direction? Do I have an R2 with an amount and a direction? Are these currents moving in the same direction? Yes or no? They are not. So that means only one of these can be the final current. Which one of these must be the final current? Yusuf?
The greater number, the larger one.
The larger value current will be the final current direction. And since 12.93 is larger than 11.12, the final direction is determined by these two cells, which came to us from what? They came to us from part 1. Trust me, you don't want to move the paper around too much. So our final direction of current through here, and I can slide this over this way, yay, is going to be to the left, yes? So for R2, it will be to the left. Is everybody okay with that direction on our, and how do I determine the final amount of current? Do I add these two guys up, or is there some subtraction involved? Yusuf?
You're going to subtract the smaller one from the greater one.
Yeah, the smaller one will be subtracted from the larger one. So I will go ahead and take my 0.93 and subtract my 11.12. And so my milliamps works out to be, what do you get?
398.2 millivolts. Sorry, wait, you're doing current?
No. We're subtracting. Oh
yeah, it's 1.81
subtracting.
milliamps. Sorry, 1.81 milliamps.
Okay, all right, you were scaring me. All right,
Sorry.
I also have
I have it written down.
1.81 milliamps. Cool. So 1.81 milliamps. Is everybody happy with that value and understand why? And now on our final sheet, our part 3 sheet, do I have enough information with a current and ohms to calculate a final voltage across R2?
Yes.
Woohoo. Let's go ahead and do that. Times 220. And Yusef, what do you calculate for the final voltage?
398.2 millivolts.
Okay, so 398.2 millivolts. How many people agree? Wave your hands at me. Thumbs up. Yes? Okay, that's good. Great. Now we have 3 more cells and we're almost there. So what we have is, let's take a look at R3. So I'm going to scoosh things around with my camera and move things in this direction and scoosh this down so I can see the value of R3 right there. And I'm now going to look at R3. And so, I think I have that, yes. There, and there. So can we see from one part of our analysis, we happen to have a current moving upwards through R3, and then we have another current moving upwards through R3. In both instances, they're moving upwards. So are these currents aiding or are they opposing? Listen carefully to the words I'm using. Aiding means they're going in the same direction, they add. Opposing means they're going in opposite directions, we subtract. So in this case, they are aiding. And so as they're aiding, can we easily tell what our final direction of current through R3 is? Clearly going upwards, yes? So let's go ahead and mark that in our paper as being clearly going upwards, like so. And how do we determine the final amount of current? What do you think, Jacqueline?
We add them.
Let's go ahead and add them. And when you go to add them, what is it that you end up calculating them to be?
11.6 millivolts.
11 point, come again? If we just add these two numbers, 2.59 plus 8.62 gives you
11.21 millivolts.
okay, milliamps. Milliamps, okay. So we end up with 11.21 milliamps. Okay, so while we have that information on the display of our calculators, let's go ahead and multiply by 330 ohms in order to calculate what this voltage is. And that works out to be what value, Jacqueline?
3.7 volts.
Precisely, 3.7 volts. Hallelujah. All right. Is everybody okay with how these values came about in part 3? So far, so good? All right. So let's review what we have gotten so far. From the original circuit that we started off with way back here, we were instructed to use something called superposition theorem. When we have multiple voltage sources, we had 3 basic steps in order to get this part done. Step 1, step 2, step 3. We algebraically, we followed step 1, and we had a part 1 VIR table. We followed step 2, we have a part 2 VIR table. We take the 2 tables worth of information, and that allowed us to combine them algebraically. Now we have a part 3. Once we get here, we need to double check our analysis to see if everything is correct. And we can confirm these values being correct. We can confirm this by doing this, confirm using two things. One is going to be KVL. And KVL was Kirchhoff's voltage law. And number two, we can also do loop voltage analysis. Okay. So Kirchhoff's voltage law, loop voltage analysis is very easily done. Let me explain what this stuff is. Our friend, Mr. Kirchhoff, KVL is Kirchhoff's voltage law. And what Kirchhoff's voltage law states is this, and I like to, a couple of things here. The voltages in any closed loop must algebraically add to 0 volts. Must algebraically add to 0 volts. So when we had a simple circuit, like so, and if I were to do something simple like, oh, I'm going to give us 10 volts here, and I'm going to make this 20 ohms, and I'm going to make this 80 ohms, and you needed to determine the voltage across each of these. Well, I made these proportional. Isn't 20 plus 80 100 ohms? Isn't this going to be 2/10 of the voltage? Isn't this going to be 8/10 of the voltage? If I go to do this, could we calculate very quickly and my RT? RT equals 100 ohms, yes? So what is my VR1? VR1 using voltage divider formula was what? Equal to R1 over RT times my voltage source, yes? So wouldn't this be 20 over 100 times 10 volts? Isn't this going to be 2 volts for VR1? Okay? Tried to keep the numbers fairly basic. And you'll find, by the same token, VR2 is going to be 8 volts. So how do I polarize what's going on in the circuit? So to keep things simple, positive here, negative here, electrons flow here, flow up through this guy, flow up, turn left, go through here, and back to the source, yes? How do I polarize my voltage on R2? The electrons tell me they must come in on the negative side and go out on the positive side. They must go in on the negative side and come out on the positive side. So if I were to go around this circle, if I were to mark things up this way, just keep this, call this A, call this B, call this C, and call this D. And the voltages that we just calculated, this is 2 volts here, and this is 8 volts here. If I were to tell you to go around in a loop, A, B, C, D, E, and draw a line, that means you're going to start at point A, and with a red probe, let's pretend we have a red probe. Do I have a red pen? Possibly. Yes, no. I have something that's almost red. Yeah, this is almost red. Okay, so I'm going to start at A and follow my probe. I'm going to encounter what polarity? Positive. How many volts across this resistor? 2 volts. Okay, so this loop will give me the following. It will give me a positive 2 volts. Then at point B, I have to continue, according to this loop direction, I have to continue from B to C. So as I continue downwards, what polarity do I encounter first? Positive. And how many volts is across this guy? 8 volts. So I have a positive 8 volts. And now I'm at point C. Now, according to my loop direction, I have to go from point C to where? D. Is there anything changed between C and D? No, that's just a wire, so nothing changes. And then according to my loop, I have to go from here, oops, there's no E, go back to A. So I'm at D, now I have to come back up to A. If I'm at D and I come back up to A, what polarity do I see here? Negative. How much volts? 10. So add a negative 10. Whoop. A positive 2, a positive 8, add to a negative 10. Do I end up in that loop of 0 volts? Yes. Kirchhoff's voltage law is absolute. It's a law. It's not a theory. It's not a hypothesis. It says must. These voltages in any closed loop must algebraically add to what? 0. And so what this does is this confirms your basic calculation of 2 volts and 8 volts as being correct in the right places, and it also confirms your polarities, which also confirms your directions of current flow. Kirchhoff's current voltage law is huge in double checking your work in superposition. So based on this newfound knowledge with Kirchhoff's voltage law, let's see how this helps us in our final analysis. In our final analysis of the circuit, we are going to redraw the original circuit. So I'm going to redraw my original circuit. Here's my original circuit. And maybe I don't have to redraw it. This is so nice. I think I'll just, no, I want to keep this blank. I'm going to redraw it. It's okay. It only takes a few seconds to do this. And you guys are worth the effort. Yes. Here, 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 here. This guy is here. We have one fellow here. We have one fellow here. Like so, and like so. So this is VS2 3.3 volts. This is VS1 of 5 volts. We have our polarities. Now the polarities of the sources are absolute. They can't change. They are however they're marked. But we do have very specific polarities across our R1, R2, and R3. At this point in time, I don't have to write in the ohms, but I should write R1, R2, and R3. What was our final direction of current flow through R1? Our final direction of current flow was to the left. So I will to the left. And what value of voltage did we calculate? 1.3 volts. So I will write down 1.30 volts. So from our final VIR, did I take the direction and the voltage right off of our VIR table and transfer it onto this redrawn circuit? So far, so good. I'm going to do the same with R2. Take a look at R2. R2 has a final direction, and it says it flows to the left. I will draw the arrow to the left, like so, which means this side is negative, this side is positive, this side was negative, this side was positive. And what was my value of voltage? My value of voltage was 398.2. I'm just going to, for round figures, I'm just going to mark this as 0.4 volts, okay? We normally would write in the 398.2 millivolts, but I'm going to keep our math simple. So it's approximately 0.4 volts. And then we also have one more direction and value to submit, that's through R3. And the final direction of current through R3 is up. So I am going to draw the arrow going up, like so, which means the bottom must be what polarity? Negative. The top must be what? Positive. And what value of voltage did we have here? According to this, 3.7. So I'm going to write down 3.7 volts. Okay, this is all the information that we need from our part 3. We want to double check. R1 was to the left of 1.3, to the left of 1.3 volts. R2 was to the left at approximately 0.4 volts, to the left approximately 0.4 volts, and R3 was up at 3.7 volts. This is up at 3.7. Let's bring back in our letters. So here is point A, B, C, D, E, and F. Now, look at the magic. How many loops do you see in this illustration? Jacqueline.
I see 2.
2. Can you call out the letters that bring us completely around one of those loops, please?
A, B, E, F.
Okay, so A, B, E, F back to A, yes? With the caller starting letter, all right? So Jacqueline called out loop A, B, E, F back to A. Does everybody see that loop? Now, algebraically, let's determine the voltages around this loop, starting at A. So starting at A, the red probe is right here. Here's my red probe. And it must move towards point B. The very first polarity it encounters is a what, Jacqueline?
Positive.
Okay, so this is going to be equal to a positive, and how many volts exist there? 1.3 volts. So far, so good. We have now moved from point A to point B. Now, according to your loop directions, we now have to go which direction?
Down.
Down to point E. When we move downwards, Jacqueline, what's the first polarity you see as we move downwards?
Positive.
So we will encounter, this will add to a positive 3.7 volts. Is that correct? We now have gone to point E. At point E, now which direction must we go?
We must go left.
Yeah, left to F, and there's nothing to reconcile there. There's no voltage, there's no component, so that's a nothing. So we don't add anything. So now we're at point F, and we have to complete the loop by going back to A. So we have to go upwards, yes? When we go upwards, what polarity do you encounter?
Negative.
A negative. And how much voltage do you encounter there?
5 volts.
So guess what? I've been writing this down as you've been calling them out. Positive 1.3, positive 3.7, add a negative 5. Algebraically, what does this loop add up to be?
0. 0 volts.
0 volts. Is Mr. Kirchhoff happy? He's not rolling in his grave, right? He's very happy. So you've proven through the first loop that he's happy. Algebraically, all the voltages in that closed loop add up to 0. What's that tell you? Not only is he not rolling in his grave and he's happy, but you should be happy, because that means your directions of the currents are correct, your polarities are correct, and the values of the voltages you calculated are also correct. Now, the next one, let's see, Yusuf, can you call out another loop, please?
Are we going D, E, B, A?
Well, if you go D, B, E, A, you're not forming a loop. You're kind of going zigzag. I need a closed loop. I need this to go all the way around. So you starting at D is all right.
I mean, I guess.
So here's D.
Yeah, so E.
E.
I don't know where to go. I mean, if we go to C, if we go B, C, doesn't it change?
Well, you're just going around a loop. You're just picking a loop.
Okay, so D, E, B, C.
All right, D, E, B, C, back to D, yes?
Sure.
Do I have another loop over here? And you're calling out the directions as being D to E to B to C back to D. Those are the 5 letters that make up that particular loop. So does everybody see the path? So from D to E, is there anything to add? Nothing. How about from E going up to B? What's the first polarity you encounter?
Negative 3.7.
Okay, so we are going to add a negative 3.7 volts. Now you're at point B. At point B, you need to be moving towards C. So what's the first polarity you encounter?
Positive.
Positive, how many volts?
0.4.
So add a positive 0.4 volts instead of the milli. We just use nice decimal there. Now we're at point C. Point C, we have to complete our loop by coming back down to D. By doing so, what's the first polarity we encounter?
Positive.
And what value do we encounter?
3.3 volts.
Okay, so we're going to add a positive 3.3 volts. So when you go to add all this up together, algebraically, what does that loop come out to be?
Net zero.
Wow. Is Mr. Kirchhoff happy? Are you happy? He's not rolling around in his grave. We've got a second loop here, and yes, you've proven by using Kirchhoff's voltage law and this loop analysis that yes, all the voltages in any closed loop algebraically must add up to 0 if the polarities are correct and if the values of the voltages are correct. Well, guess what? Your polarities are correct because they were guided by the directions of your arrows, and the values of the voltages were correct because of your analysis. So we're happy. Wei Ji, can you see another loop? Can you see another loop? We already did this loop. We already did this loop. Any other loop?
Nope.
No? Okay. Jacqueline, are we done with the loops? You see any other loop?
I see a loop.
What do you see?
A, B, C, D, E, F, A.
Whoa. This big old thing on the outside? That's a loop. That's a valid loop, my friends. This big old thing on the outside. So we're going to call that out. Loop. A, B, C, D, E, F, back to A. That's a big, long bunch of letters. But let's see what happens on this outside loop. Jacqueline, we're at point A. We are now moving to point B. What polarity do you encounter?
Positive 1.3 volts.
Okay, so we're going to start off with a positive 1.3 volts. 3.0 volts. Okay. At point B, we're going to move towards point C. So what polarity do you encounter?
Positive 0.4
And what
volts.
value? Okay, so we're going to now add a positive 0.4 volts. You are now at point C coming down. You are going to do what? Add a...
Positive 3.3 volts.
Okay, so now we're going to add a positive 3.3 volts. You are now at point D. And to point E, what do we add?
Nothing.
Nothing. How about from E to F? What do we add?
Nothing.
Nothing. And how about from F to A? What are we going to add?
Negative 5 volts.
We're going to add a negative 5.0 volts. Wow. Let's go ahead and do that. This works out to be 1.7, 5.0, negative 5.0. Guess what? Does this outside loop give us a 0 volts as well? That's exciting, my friends. This has proven, you have proven your final voltages, your final directions, your final polarities in this final draw as being correct, because each of these loops algebraically adds to 0 volts. And where did these values come from? These values came from our part 3 of our analysis, Where did our part 3 analysis information came from? It came from us analyzing part 1, analyzing part 2, and then algebraically adding up the values to give us part 3. What do we do with these values in part 3? You draw them back into the original layout of the circuit, and I would recommend drawing a clean big circuit like this. Don't use my original one here that we started off with, because this might be a little small. And I don't need the ohmic values, so they really just get in the way more than anything else. So this is nice and clean. I just R1, R2, the polarities, the directions. This is great. So now that you have a lecture that pertains to superposition theorem, are the exercises now a little easier to understand? I hope that they are. And since they were assigned some weeks ago, accidentally in the wrong place, I will refresh them and put them into our current week's work. And that will be due come Monday. Is that all right? I will post this particular video. And in addition to this video, I think I have 2 other superposition videos, but I like this one the best. I like this one the best because I'm using more paper than I've ever used before in the previous ones, not only in the VIRs, but also in my circuit redraws. So in one circuit redraw, we have this particular illustration, and in another circuit redraw, we have another circuit illustration. We also have an explanation of Kirchhoff's voltage law. So I really like this particular one. So that being said, you also have the DC Circuits Challenge that I hope everybody should have completed by now. So the DC Circuits Challenge was 10 exercises, 10 points each for a total of 100 points. And so what you should have uploaded for that particular challenge would have been your certificates. So if that hasn't been completed yet, please make sure that that is completed. Please keep an eye out for Discord and Canvas for additional messages for anything else that we want to prepare for Monday, all right? Any questions for me before we sign off?
We discount the very beginning where you modified the board. We're not modifying our voltage source for the breadboard, right?
No, I don't want you to do that until I do some further experiments. What Yusuf was talking about was this particular circuit here, and I'm just playing around. I know that in theory, we can certainly do our superposition analysis. I wanted to see if whether or not the 2 voltage sources would be antagonistic to each other, whether they could coexist happily on this board or not. And I'm running into some interesting glitches. But what I've got, my friends, is this circuit here built on this board. If you look at it carefully, I've got the 100 ohm resistor here. I've got the 220 ohm resistor here. I've got the 330 ohm resistor here. I've got the power on this side of R1 from my positive rail of 5 volts. So there, this powered off of here, and this jumper is set to positive 5. I've got the this side of R2 right here tied to the positive side of my 3.3 volt source, which is loop down here to this red rail, and this red rail is now set to 3.3 volts for positive. And then the grounds are all connected together. So the ground of the 5, the ground of the 3.3, and this middle resistor are all tied to ground. So if you look at this middle resistor, I'm using this blue rail as ground. This blue rail is ground to here, and then this comes up to this ground rail up here. So don't do this yet, because if I run into difficulties or challenges with respect to these 2 sources seeing each other, I don't want you to blow up your power supplies. I don't mind me blowing up mine, but I don't want you blowing up yours. So I just wanted to see if I could actually build this and have everything be appropriate. If I can get this to work confidently, then I will ask you to go ahead and do this, because this really brings together our analysis of this onto a breadboard if I can get both of these voltage sources to work. So Yusuf, to answer your question, since you saw this since the very beginning, no, don't put this in your board just yet. Let me play with this a little further and I'll let everybody know. Is that all right? Okay, my friends, one last thing. I'll take your happy smiling faces and then we'll sign off. Yay, let me get my camera back off of the board. Here I am, there you guys are. And oops, let me go to gallery view. Don't want to see just me, thank you. Gallery view so we can see, oh, look at this. We have the little fur ball. Yay, fantastic. Hello, fur ball. What's the fur ball's name? Kiki. Her name is Kiki. Oh, how pretty. All right, give us a smile. 1, 2, and say cheese, yes. Good job, everybody. All right, fantastic. God bless you all. Have a lovely week. And we will see you on Discord and Canvas. Adios.